Thank you for introduction. So I'm Jungmin Bae from Post-Texas, Korea. And then I'm going to talk about some symbolic reachability analysis technique using narrowing and heuristic search. Yeah, of course, I'll introduce what are those things. Yeah, so for some context, yeah, obviously, distributed systems have a central role in safety-critical systems because, of course, many safety-critical systems, including cyber-physical systems, distributed systems. And of many formalisms, rewriting logic, also shown this morning by Laura, is a highly expressive and executable formalism that's widely used for distributed systems. As many formalisms for distributed systems, including actors and patterns, can be naturally expressed in rewriting logic. And also, it supports various formal analysis methods, including reachability analysis and LTM analysis. Oh, by the way, can you hear me? Okay, okay, good, thanks. And then also it provides some languaging tool called mode. And then in this paper, we are going to propose a new formal analysis technique. And for that reason, already briefly introduced this morning though, but I'll introduce very briefly what is rewriting logic. So basically, in rewriting logic specification, we specify state as some term in some algebraic data types, like lists or sets and so on. And then transition of the system is given by rewrite rule, which is a pattern of terms. So basically, if say some state that matches pattern T can go to T prime in the next state. So I'm going to use, okay. So for a simple example, if we consider this rule where F and S are constructor symbols, where N is some pattern variable, then some term, right, like that F(S0) could be written to, yeah, as you expect, yeah, F(SS0), because this S0 match N, and then the right hand side is S0, right? So it's a very simple mechanism. And then I'm going to show some running example that will be used in this talk. Not in the paper though, but the example used in paper is more complex. That's why I'm going to use different example. So it's a very simple mutual exclusion algorithm here, often called ticket algorithm. This is widely used in real life, right? So in the bank or a bakery. So there's one server, right? And then there's a number of clients. And then only one client can be served at a time. Therefore, there's some ticket dispenser machine. And each client take a ticket, and then having some ticket number. And if server call that number, then this guy will serve. Right. So in rewriting logic, we can specify each state is some term. So here, for simplicity reason, we consider each state as a triple, where n is the current number in the ticket machine, and the m is the number currently served, and a set of processes. Each process has some status. It could be idle, or waiting with some ticket number, or being served with some ticket number. All right, and then we can easily specify rewrite rules that easily describe the description in the previous slide. So the first rule in the model syntax, fortunately, the syntax is introduced this morning. Right? If there is some process is idle status, then goes to wait status is ticket number, where this number is used, which is the current number. And then after the status changed, this number is increased by 1, right? As expected. Here we choose to represent number as a set of S symbols. So 1S is 1, 2S is 2, and so on. And then if some process has a ticket M, and then if it match the second component, then it goes to critical section. And it can freely exit to ideal status where the second number increases by 1. It's a very simple specification. Yeah, of course, some atonicity is assumed, but I guess it's good for illustration purpose. Okay, and we can now perform several analyses. For example, if we consider only one process, yeah, it's just operation using purpose. We can by applying make rule, can go to reachable, right? Where 0 is increased by 1, and then by code, change to crit, and then by applying action rule, now the second component decreased by 1, and by the answer. All right, so of course now we can perform on the checking, although there's one problem. Because these two counters are unbounded, so this is infinite state systems. And actually there's many techniques to deal with this problem in practice for various formalisms. And for Euratom logic, we can consider some symbolic representation. So one way to symbolically represent infinite several states is to use some term with logical variables or patterns. For example, if we consider this pattern, then it represents a set of any states. The first and second counter the same, where PS just denotes the several processes. So it presents infinite set of concrete states. All right, so given that setting, we wanna, as usual, perform some symbolic execution and then generate all possible symbolic states. And that technique is called narrowing in Euratom logic. It's not narrowing in abstract interpretation, but just a totally different concept. The keyword narrowing is originated because it narrows the pattern, basically. So basically, if there's some instance of this pattern can be rewritten, then there's a narrowing from different. And for example, of course, and you can define symbolic transitions between these two symbolic states. So for example, given this term, where n and ts are variables, you cannot perform rewriting in this rule because this is not match. This is actually more general than this term, but this is not instance of this left-hand side of rule, so cannot be rewritten. But an instance of this term, for example, this guy, can be rewritten using this rule. So therefore, there is a narrowing sequence from this state to this state is possible. And of course, there could be infinitely many potential narrowing because you can consider any instance. But as expected, you only need to compute the most general symbolic states. And therefore, under a certain reasonable assumption, the narrowing can be a finite branching. So with finite number of narrowing, one-step narrowing is possible from given state. And then, for example, for bakery systems, two processes. Now you will have 9 symbolic states. So we can verify the mutual exclusion because there's no two correct states in this graph. And for arbitrary number of processes, it's also possible if you consider another extraction method, which was presented in another paper, at this paper too. So basically now, based on this concept, you can use some narrowing-based reachability analysis. Just breadth first search. So basically, we use Q, right? The perform narrowing, and we remove all redundant states here, and then keep the most general explore state, and so on. So just BFS strategy. And then in the shown there is a reputation complete. That means if there exists a counterexample, then this algorithm will find that counterexample. Though this is also semi-algorithm because the termination is now less guaranteed because the symbolic states are infinite. So if we use some abstraction method to keep the number of states finite, then you can verify the absence of errors. Yeah, so far looks good. But there's some limitation of existing algorithm here. So it's actually bad at finding a counterexample because, as expected, if we consider abstraction method, then it will generate spurious counterexample. So we need some refinement, which is not proposed yet. And also, by performing breadth-first search, it will create huge number of userless states because we have to compute all the instances, although it's most general, but all the instances for narrowing. Therefore, by taking weight rules repeatedly, we can have this guy in the next state. And here, we can also perform this weight rule for this instance of this variable. So that is instantiation again, and this variable can be instantiated again and so on. So the number of processes in this sequence will be huge. And then, as you expect, therefore, number of symbolic states to be considered to be also huge. So therefore, it's not that good at find a counterexample. Yeah, of course, we can apply abstraction, but then problem express counterexample. And then some observation is that actually it increases the complexity of patterns all the time. And therefore, we want to avoid this issue. So that's the motivation of this paper. So basically, you want to avoid these complex table patterns. And then the most intuitive way of doing that is, as usual, consider some heuristic search. So this is a modified algorithm. So all the difference is that we use priority, and priority defined using scoring function. Yeah, too simple, right? So if it's the all, then of course this could not be presented here, right? But there's some issues actually. So one is that what would be effective scoring function for narrowing? Yeah, of course, this kind of heuristics or scoring functions are very important for depends on applications, right? So here we consider generic symbolic analysis using narrowing. So it would be good to have some methodology for this purpose. And another problem is that we consider verification. So we want to still keep verification complete. Otherwise, cannot guarantee anything about this algorithm. So for the first question, as I mentioned, our goal is to minimize the complex table patterns. So it's very tempting to define the scoring functions based on complex table state or symbolic states. So a simple methodology is as follows. So this is a generic methodology for just heuristic functions for just heuristic algorithm. We just follow existing methodology where we have two scoring functions, G and H. Where G is the important one, and H is a more heuristic functions. So we choose G as a complex table pattern. For example, the term size. Yeah, not necessarily always term size, but term size can be used. And then H is an additional heuristic estimation to use some prior knowledge. For example, for mutual exclusion of the bakery system, we already know that there should be some weight processes. So in that case, the number of weight processes could be used, right? So and so. But as I mentioned, even though you can use this kind of methodology, there's some caveat. So I show some problem using this example. So if we choose this core as a number of processes in the logical symbolic pattern, then yeah, even though this is not ideal initial state, but let's use this initial state to counter 0. Then yeah, there's infinite sequence that only perform narrowing for this first process. Yeah, and then I mentioned this and not that good choice, but and these two are concrete terms. So there's no folding or some assumption. But the heuristic search will only explore this path because this is the minimal scores anyway. So the problem is that now the heuristic neural search will never visit symbolic state is highest scores. So it's very problematic. Then question is that how can we avoid this, or is there any condition to ensure there's no such thing happens? Actually, it's quite simple. So the only thing needed to avoid this sequence. If there's a given any score value, if all the reachable logical patterns, whose score is less than this guy, is finite, then obviously there's no such infinite narrowing sequence possible. Therefore, the reputation complete can be guaranteed, and then we have proved this in our paper. Okay, so there's another caveat explained in the paper, but due to time limit, I'm going to skip that. Okay, so we apply this technique to some reasonably complex consensus algorithm. It's called the one-third rule. There's an n, as usual for consensus algorithm, there's n processes or n nodes, and each guy sends message or broadcast message to all other nodes. And then if each node receives 2/3 of the entire node, then the new value is set to the smallest, most frequently received value. And then if more than 2/3 of the received value in the network are XP, then it decides to XP. So it's proven, another paper, now of course not our contribution, that this algorithm will eventually agree on the value if the algorithm terminates. Because this algorithm considers faulty communication, therefore this algorithm may not terminate. But it's terminate, is guaranteed to agree. And here important parameter is here is 2/3. Is actually why the name of this algorithm 1/3. Here this 2/3 is a decision threshold to proceed to the next round or to determine the value. So the simple question is that what if we use a different decision threshold, say half? Then actually there is the counterexample. Okay, so one interesting question is to perform this narrowing-based approach for this 1/3 rule is different decision threshold for arbitrary number of initial states. And then probably as you expect, it's fair to find the counterexample using DFS original algorithm because the number of symbolic states repeatedly grow due to the exact reason I mentioned in the previous slide. For example, even after only 6, number of states explored is 5,000. And actually, it requires more than 19 steps to find the counterexample. So it's hopeless. But we can apply heuristic score algorithm that is much more feasible. So we consider two heuristic functions. One is just considering complexity. And next one is a bit more complex, but using some prior knowledge. So they add some heuristic factor. And then the experimental result shows that given timeout for 28 hours, if you use the DFS to replace its timeout, if you use a score 2, it's a 10 final counterexample. So it's for 25,000. And then if we use more prior knowledge, then it can be try the counterexample within 20 minutes. So this shows that, of course, we only show only one example, though, but it shows that this combined heuristic and narrow research could be quite promising. All right. So, the summary. The rewriting logic is quite powerful framework, and then the symbolic reachability analysis using narrowing is some promising technique. But the previous problem is that it's not that good at finding counterexample. So the contribution in this paper not fully explained in this talk. You can check the paper if you're interested. As I mentioned, we proved sufficient conditions for this heuristic narrowing search to preserve reputation complete. I think that's our key contribution. And then we presented a simple methodology to design these correct scoring functions based on that. And then, although not mentioned in this paper, but in this talk, but as you can expect, we have implemented a prototype tool. And then we demonstrate the power of our approach using this one-third rule consensus algorithm, which is much more complex than, of course, this bakery example and the many parameterized protocols. So it's simpler than left algorithm, but still quite complex. So the ongoing work is to extend this algorithm to combine this technique with SMT and then more optimization. So, all right, so I think it's all, and it's 22 minutes, so it's fine. So thank you.
Oh, so we have definitely got time for questions. So, any questions?
Yeah,
Well, yeah, in your example, you had the same pattern that is repeating again and again. If you do, say, sequence of conditions, couldn't you express it as something symbolic again? Because the change is the same along the pattern.
So you mean the pattern? Probably I missed something from your question. So you mean the pattern?
Yeah, here, say you get, well, when you have S, yeah, you get 3 times S,
yeah. So
2 times the 0, and then it's the same thing. There's just a difference of 1.
yeah. Of course, this is some artificial example just to show some problem. So
Yeah,
this is, as I mentioned, this is of course bad initial state. So ideally, better initial state would be this guy.
Yeah.
So if we just use
Yeah,
N and
exactly.
IS, then there's no problem. But our goal is basically to present some methodology that's independent from such patterns. Therefore, we consider some potential, although it's stupid example.
Yeah, but what I meant is that it looks like some transition environment where you have wait, crit.
Yeah, exactly.
And maybe you could reuse that. So that was one thing. And the other thing is that you're using BFS, breadth first search.
Yeah, that's a actually original algorithm used in both.
Yeah. And well, here we can easily see that you have an infinite sequence in depth. You could consider also to have an alternation of depth and breadth first.
Oh, actually, that would of course possible, and then it's actually controlled using, although not mentioned in
Using
this
the
paper.
scoring function.
Yeah, exactly. Actually, in this experiment, we use score 1 is actually BFS, and then not mentioned, and then also you can define different scoring function to do exactly what you said. But yeah, of course.
Okay. Thank you.
Cool. Yeah, thank you for the questions.
questions? Oh, I actually did have a question. So if we go back to the infinite state that you were showing before.
Okay, this guy for heuristic.
Yeah. So it does say, essentially what you do is you prevent having an infinite trace.
Yeah,
So how do you detect the infinite trace?
So of course, some automatic technique could be possible, but here actually some the most precise this scoring function is possible. Is actually the size of the logical term. Yeah. If we set this G as the size term size, then of course the number of terms whose size is less than specific number is finite, assuming of course there's a finite number of function symbols. So here size is
so you can determine the number of steps before you've exhausted all the possibilities. Is that what you're saying?
So here the term size means, for example, not all possible instances, but the pattern itself. For example, here the size of this pattern is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can actually easily limit the term size.
Right. So, but fundamentally you determine a maximum depth, a number of steps that could be taken, and after which point you decide it's infinite at that point. Effectively.
Yeah. So of course there's some caveat again, because this h could be another function that violates that kind of thing, so that have to be careful.
Right.
Yeah, but it is to find such a G practice.
Cool. Great. Okay. Any last questions? Cool. Okay. Well, thank you very much.
Okay. Thanks so much.